Takayuki, maybe he's in one of the breakout rooms. Okay. Well, welcome back. We're waiting for Takayuki, who is going to chair this session. So if you haven't had too much of me already, I'll just introduce the papers for this session so that we can keep the time going, and hopefully Takayuki can join us soon. So the first paper we have for this session is by Iman Yeckehzaare. Apologies for the pronunciation. Iman, are you there?
Yes, I'm here, and that is a good pronunciation.
Oh, fantastic.
Perfect.
You are welcome. Yeah, whenever you're ready, we'd love to hear more about your research.
Sure. So should I start presenting, or I should wait for the host?
No, I think start as soon as you're ready.
Okay, sure. So I followed PI and CSCW norm, and I recorded my presentation video. So I'm going to play it for you, and then I'll be happy to answer your questions. Do you see my presentation?
Yes.
Okay, let's start.
I am Iman Yeckehzaare. On behalf of my co-authors Elijah Fox, Sam Wood, and Gail Grot, I present One Academy, a platform for collaborative note-taking and visualization. This project is advised by Professor Paul Resnick at the University of Michigan School of Information. Multiple studies have proposed collaborative note-taking system. Kam et al. In 2005 introduced live notes and found that notes taken collaboratively were more comprehensive and encouraged dialogue between the students. Stamel et al. In 2008 designed CoScribe, a novel pen and paper based system for collaborative annotation, linking, and tagging of digital documents. Mayaki and Matsukawa in 2013 implemented FreeCoNote, a platform for collaboratively building links between notes, which helped the students learn complicated concepts. In 2021, Costley et al. Questions the effectiveness of collaborative note-taking. They argue that most previous studies that claim increased learning performances through collaborative note-taking have speculated that sharing this task among group members may reduce the extraneous cognitive burden placed on each member. They conducted a study with 171 students in a flipped scientific writing course to measure the effects of collaborative note-taking on cognitive load. They divided the students into two groups. One was instructed to take notes collaboratively, and the other group was not. Those who took notes collaboratively reported higher germane load, which means understanding of the course content, but they also reported higher extraneous cognitive load, or confusion. So the question is how to design a collaborative note-taking experience that improves learning while maintaining coordination and consensus to reduce confusion. To achieve this objective, I developed One Academy and incorporated these four mechanisms in its design. One Academy encourages taking small notes, each about only a single concept or granular piece of knowledge. When creating a new note, the students have to first identify and link the other notes that should be learned first to be able to understand this new note. We call these prerequisite links. All notes and links are organized in a single large map that connects concepts from different disciplines. They are visualized to inform the community about the learning pathways formed by sequences of notes that one needs to learn to be able to understand a target concept. Since there are many notes, One Academy enables the students to personalize their view of the map to prevent learners from getting distracted by notes that they're not currently studying. To support coordination and consensus, no one can directly modify the map. Instead, collaborators propose changes and the community votes on whether the changes should be implemented. To motivate members of the community to propose changes that are helpful to others, contributors earn reputation points through votes on their proposals. This is my personalized view of One Academy. I can zoom in and out and navigate through the nodes on the map. This node defines confounders in causal inference. All of these nodes are collaboratively generated by a student. The nodes classical epidemiological definition of a confounder, causal definition of a confounder, and the confounding in causal inference are children under the same parent node, confounders in causal inference. This means to learn these three, one first needs to understand this node. This other node explains the confounding in causal inference can be done when the confounder is measurable and unmeasurable. Other students have explained how to deconfound a measurable confounder in this node and an unmeasurable confounder in this other node. Sometimes a node requires multiple prerequisite links. For example, to learn deconfounding in a regression model, one needs to understand both regression models and deconfounding a measurable confounder. To propose any new node, one has to first identify a parent node and link the new node by a prerequisite link. This ensures coordination and development of learning pathways. It also reduces redundancy among nodes. After finding a direct prerequisite node, one can clearly see if a node already exists and can propose an improvement to it if necessary, but cannot propose duplicate nodes. The students can also vote on how helpful each node is to their learning. We can tell that 7 people have upvoted this node and no one has downvoted it. To encourage the students to create helpful proposals and nodes, there is a reputation system. Upvotes and downvotes on proposals and nodes result in gaining and losing reputation points. The members' reputation points in each community are made identifiable through this community leaderboard. This node has been revised over time through 16 different proposals by students in the community. In the list of accepted proposals, we can click different versions to see how the node has evolved over time. Before a proposal can be accepted, however, it must be reviewed and voted on. To improve coordination and consensus, I implemented a popularity-dependent approval mechanism. For a proposal to be accepted, it must receive at least half as many votes as the node it was proposed on. This means that it requires more consensus for a proposal to be accepted on a node with more votes. I designed this mechanism to prevent spurious edits on nodes that have been voted as helpful to the community, while making it easy for nodes that have not been found very helpful to be improved. There are more than 22,000 nodes collaboratively generated on One Academy through more than 58,000 proposals. It would be very distracting if one wants to see all of these nodes at the same time on their map. To improve focus, One Academy enables users to personalize their map view by hiding and opening nodes. This diagram shows the number of proposals contributed over time. One Academy is currently being used by 13 learning communities on topics ranging from political psychology to Bayesian statistics to UX research. Registered users are mostly graduate and undergraduate students representing 133 different colleges and universities around the United States. There are currently about 400 active users who joined One Academy for collaborative learning and research and not associated with any courses. Our structural equation modeling analysis of the activity logs shows that the students found collaboration on One Academy helpful to their learning. In this analysis, we compare nodes with proposals from more collaborators with those with fewer collaborators. We define the outcome as cumulative upvotes minus downvotes by non-collaborators on each node. The results indicate that while number of proposals did not significantly affect the votes, number of collaborators on a node is correlated with an average of 0.6 more upvotes from non-collaborators, indicating that the node better help with their learning. This means that the more unique collaborators on a node, the more helpful the students find the node. In this analysis, we control for possible confounders such as the average performance of collaborators, number of students who viewed the node, total number of interactions with the node, number of prerequisite links on the node, total number of proposals on the node, and the lifespan of the node. We interviewed 30 users who have been using One Academy for at least a month, and using grounded theory conducted a thematic analysis of their responses. The students shared their screen showing us their personalized map. Most of them explained the helpfulness of the process of breaking down their knowledge into small nodes and then constructing learning pathways through forming prerequisite links. Some spoke about about how they find this helpful for their understanding. Others reported about the helpfulness of the metacognitive processes when creating new nodes. The students also spoke about identifying gaps between nodes. When nodes are poorly linked, interviewees showed us how they proposed edits to improve the organization of the learning pathways. The interviewees also showed how they reviewed learning pathways designed by others and why they found them helpful. They found the pathways as a means for guiding their learning and to discover new interests. I encourage you to check out our YouTube channel to learn more about One Academy. Thank you for listening.
I'm ready to take questions.
Excellent. Thank you for the presentation. That was very interesting.
Sure.
Does anyone have questions for Iman?
I don't know if you hear my background. There is a heavy rain here, so sorry for the background noise.
That's okay. That's okay. It's not coming through. Okay. Can I ask one question then? If you did
Sure.
a grounded theory study, did you get any sort of suggestions? Because those were very positive things that you described, but presumably there was some sort of formative feedback in terms of what you should do differently or some of the things that you might change or build on top. What were some of the sort of changes that you got inspired by?
Very good question. So we are still using a prototype version of One Academy, although we have a fair number of users using it from different schools in the US, but it is still a prototype version. And what that means is sometimes when you look at like how I interact and use One Academy, sometimes like you see lags, you see like when multiple people are working on the same node, sometimes they get distracted. So there are some nuances in terms of technical implementation that we need to work on. But in general, these students who were mainly voluntarily using it, they found it helpful for both learning and their collaborative research. So they're not researchers necessarily. Most of them are undergraduate and like graduate students from different schools who are like creating communities on different topics. And they get to know each other, like people get to know each other from very different schools, and they get to know about the research topics in different schools, and they share it with each other. So the basic idea is that whenever they learn anything from reading a paper or a chapter of a textbook or whatever, they come to One Academy, they share it as like these small nodes and relationship between these nodes. Yeah, most of the negative feedback we have received from participants so far were technical issues that they keep asking to resolve and to add new features. So for example, private chatting or like sharing their videos in the chat, and a lot of new features that they ask. But in terms of in like crowdsourcing process or the popularity dependent threshold that I was talking about for accepting or rejecting proposals, we didn't receive any feedback about those topics.
That's great. Thank you very much. There's one comment from Ben Town. It just has to do with keeping the gaps in the recording, just so that it's kind of easier to follow. But I'll leave you follow up with that. But otherwise, that's fantastic. We'll do the same thing. We'll add a link to the LinkedIn where anyone who has more questions can contact you there. So thank you very much.
Thank you.
Next, we would invite Chen Chou, and who's presenting some work that she has done with her colleagues.
Well, that's really
Yes.
Takayuki.
Okay. And that's
keep it for the end.
Takayuki. Yes, sorry. So that's actually on Takayuki's paper. So if he's not here, we'll do the same thing. We'll move him to the end, and we'll skip forward one in the order. So Avel. Avel, are you there?
Hello.
Oh, Hey, how you doing?
I'm doing fine, thank you.
So thank you very much. Whenever you're ready, oh, sorry. Yes, whenever you're ready. Thank you.
Can you see the screen and understand me correctly?
Yes, yeah, perfect.
Okay, let's go. So I'm going to present the role of active inference in modeling, grounding, and studying collective intelligence. Our expectation at the Active Inference Lab is that active inference will serve as an iterative principle in the study of intelligent systems, and we want to prove it using a computational model. We'll go through 3 steps. First, show what active inference is from first principle to its application to collective systems. Second, why we expect it to be good at modeling intelligence. And third, what modeling step we'll take to make our point. First, active inference derives from a result known as the free energy principles, which states that any dynamical system that has sufficiently regular boundaries will self-organize so as to minimize the free energy of their boundary states, which effectively means constrain the future uncertainty of its behavior. And active inference is a computational framework that uses versional free energy minimization as an explicit model of how agents behave at cognitive, developmental, and evolutionary scales. So it has one interesting feature. Unlike most reinforcement learning-like models, it does not separate between pragmatic goals and drive for exploration and knowledge. Because versional free energy is equal to energy minus entropy by definition, and this is equal to risk plus ambiguity. So risk is your vulnerability to external changes in the world, and ambiguity, your lack of knowledge about what causes changes in the world. And for mathematical reasons, it is superior, it upper bounds the future surprise, which allow systems to minimize their future instability by minimizing both risk and ambiguity. It has been used as a way to model several collective systems, from ant colonies through the mechanism of pheromone communication to humans' niche construction through mechanisms of collective altered attention regimes. And it has been used as a practical way to build better ways to collaborate. The core path it takes is to build statistical dependencies where you need some, like a single structural database that tell people what to think, what to understand several terms, and to build, on the contrary, boundaries between subsystems that need to function independently. So the question is now, why do we think it is useful to study intelligent systems? First, let's talk of intelligence as a syntactic process. Intelligence, it entails the multi-scale integration of information in systems, because an intelligent system needs to be able to react differentially to different kinds of stimuli. It needs to build new way to understand its world. And this has driven neuroscientists to postulate that intelligent systems must be self-organized near what they call a critical phase transition, which presents these syntactical features. And it is true that in the brain, if you look at either structural or functional networks, you will have scale invariant structures, which is communities within communities within communities, which is something that critical systems present. So it correctly predicts the broad structural features of intelligent systems, but it does not explain either how or why we should expect these systems to build semantics, to actually understand something and to enact their structure in their own ecological niche. This is where active inference comes. Active inference explains precisely why systems must self-organize toward enacting something in their niche. because the very process of skill agency allow the system to embody information about its environment and then to, well, build understanding and knowledge about it. An interesting feature of the Inference framework is that it is not about only beliefs as only cognitive states. The agent itself is a model of its environment. Its own bodily structure is the knowledge that brings it to do things in the world. So this is interesting because Actinf allows to integrate all of the scales that participate in building an agent's phenotype. All chemical scales that allow feedback, that allow to change an agent structure, which is either through genetic selection or learning or niche construction, they may participate in versional free generalization, and they are part of the picture in the Actinf framework. So we have a picture of how cognitive agents work that encompass basically all possible feedback systems in their constitutions. So Actinf is pretty good at talking about intelligence because it explains why exactly we should expect intelligent systems to understand reality and to enact things in the world. It sketches how to integrate several chemical scales which participate in the process of building intelligence in systems, and it correctly predicts what intelligent systems should look like architecturally from the principle of variational free energy minimization. So now, what about bringing it to collective intelligence? Our goal is to basically model a brain, a collective brain made of agents, as a society of Actinf agents. What we want to know more precisely is whether we can set up a society of Actinf agents so that they collectively build multi-scale information architecture of the same kind that allow information processing in brains and other intelligent systems. The three core constraints we have is our micro model must be sufficiently minimal to model either neurons or humans. It must only be an Actinf agent and have no mechanical hypothesis on how this agent embody information. The model must allow for the evolution of a multi-scale structure that actually embodies information about the world. And we must not impose semantics into the system so that we see how it builds meaning and how it is reduced in its architecture. So we need basically two components for the model to do that. First, an Actinf agent with a minimal sandbox game to do things. Then a way for Actinf agents to interact and to learn from each other and to pick interaction from who they learn more from. And then some sort of collective action that will basically define the system fitness from a composed function of the behavior of some but not all of the systems. Our strong expectations is that this will efficiently build a collective brain, and this collective brain will be pretty good at solving collective action problem by building a multi-scale information integration structure. So more precisely, our prediction are the following. We expect critical-like behavior with scale invariance and wild dynamics to emerge. We expect the system in autonomous condition to show very rich information dynamics, whatever is the measure we introduce to measure it. And we expect the system to be better at integrating information about its niche. That would be an equivalent critical-like system. So we'll now try to sum it up. The first thing to understand is that Actinf provides a physics-centered formal ontology for how cognition occurs across dynamical and temporal and spatial scales, and more generally, how intelligent systems self-organize. Our core hypothesis is that it can provide an iterative framework to study the emergence of intelligence in collective systems from this skilled agency picture that is enacted across scales into a system's very structure. And what we expect this to mean is that active inference would be, in addition to be a good physical model, it would be a good instrumental model to build better ways to collaborate, better ways to integrate information across scales, and better ways to enact collective intelligence. So I'd like to thank the Active Inference Lab, in particular Vijay Blonite, Peter Thestrup, Wad, Amit Singh, Alex Redkin, and Brenak for their participation in this presentation. And I'd like to pass a message that I'm looking for a PhD in the emergence of urban systems and the role of collective intelligence and active inference in that. So you have a nice bibliography that you can look up when Daniel posts the slides. Thank you for listening. That's it.
Okay, thank you very much for.
And I've forgotten the video.
Perfect, thank you. So do we have some questions or some comments for Avel? And I think Daniel is there as well.
Yes.
So you also provided some links to the lab where you're working on these things.
Yes, exactly. It's the Active Inference Lab. It is a participative research laboratory on the Foundation application of Active Inference. It was funded by Daniel like 1 year ago, I think. You can maybe elaborate on this if you'd like.
Yeah, that would be interesting. Thank you.
Daniel, do you understand us?
Oh, sure. Just to say that at this collective intelligence conference, we're all interested in new platforms, new tools, new ways to analyze and catalyze collective participation. So of course, we're seeing rapid changes to the way that science is done. Like later on, there'll be a citizen science conversation. So emerging out of active inference as a scale-free framework, along with several others, we wondered about how we might be able to apply active inference as a modality of organizing a participatory science endeavor. So if anyone's interested, they can check it out, or we can continue asking questions here.
That's perfect. Thank you very much. We'll do the same thing. We'll continue the conversation. If anyone has any other questions or they want to come back to you on something, there's a LinkedIn thread there. Thank you very much. Okay, fantastic. So we have another talk now. Again, I don't think Takayuki is there unless you are. Nope. Perfect. So Payam.
Yes, I'm here.
Hey, how are you doing?
Sure.
Excellent. Thank you. Whenever you're ready, we'd love to hear more.
All right, so I'm going to share my screen first. So are you able to see my screen?
Yes, perfect.
All right. Hi, everyone. My name is Payam Aminpour. I am a postdoctoral research fellow at Johns Hopkins University in the Department of Environmental Health and Engineering. I also have a joint affiliation with the United States National Institute of Standards and Technology. Today, I will be presenting one of the chapters of my PhD work about the bonuses that knowledge diversity can produce for solving real-world complex problems. This chapter of my dissertation has been published in PNAS, where we explored the relationships between knowledge diversity and crowd wisdom once pooling local knowledge of stakeholders of natural resource systems. All right, let's get started with a little bit of problem definition. Despite the fact that emerging technologies have provided humans with enormous potential and unprecedented opportunities for producing new forms of collective intelligence, there is still a gap in the application of these approaches for addressing the contemporary complex problems facing human societies today. Problems like anthropogenic climate change, ecosystem degradation, overexploitation of natural resources like ocean fisheries, and so on and so forth. These problems are complex and embedded in systems wherein humans and natural environment are highly coupled. These are called coupled human natural systems or social or ecological systems. However, many of these systems lack adequate information and scientific knowledge about resources, local users, and their complex interactions, especially in data poor situations, which are essential for understanding the dynamics of these systems and how they function. Our approach to addressing these problems is built upon theories of collective intelligence, particularly the wisdom of the crowd, and is also inspired by this quote from Elinor Ostrom, a Nobel Prize winner in economy. There is no reason to believe that bureaucrats and politicians, no matter how well-meaning, are better at solving problems than the people on the spot who have the strongest incentive to get the solution right. The local stakeholders, or as Elinor Ostrom said, people on the spot, have routine interactions with their local environment through day-to-day activities like fishing, hunting, farming, or being responsible for managing the resources. Therefore, they are more likely to hold valuable knowledge about such systems through their day-to-day interactions with these systems. In this study, we used an example of striped bass fisheries in Massachusetts to ask whether we can harness this local knowledge and understanding of stakeholders about human environment interactions and aggregate them to accurately model natural resource systems wherein common pool resources are used or managed by diverse groups of stakeholders. Participants used an online cognitive mapping technology called Mental Modeler to create a digitalized graphical cognitive map representing their individual knowledge or mental models about causal relationships between social and ecological components related to the striped bass population in Massachusetts. For example, how increased fishing activities influence striped bass population, or how increasing water temperature would impact fish habitat quality, and so on and so forth. Participants independently built their own cognitive maps with no influence from researchers, facilitators, and other participants. We collected data from 3 types of stakeholders: recreational fishers, commercial fishers, and local fishery managers. Here we hypothesize that a pool of local knowledge from diverse stakeholders may outperform homogeneous pools in conceptually modeling and representing complex social ecological relationships, because diversity helps them produce collective intelligence, or what Dr. Scott Page refers to as diversity bonuses. We also assume that individuals within each stakeholder type construct cognitive maps or mental models that are more similar to one another than to members of other stakeholder types. This is called modular structures, meaning that there are subgroups of individuals within the sample whose knowledge and perception are more correlated, similar to one another. In such cases, the collective wisdom can be improved if the aggregation takes place in 2 levels. First, aggregating responses within the module, followed by subsequent aggregation across the modules. So we first aggregated the cognitive maps of individuals within the same stakeholder type or modules. This produces the aggregated maps of 3 homogeneous pools. Each map is a unique model of social ecological relationships that represents the collective knowledge of a particular type of stakeholder. Green nodes are ecological components and purple nodes are social components that are interconnected using a set of positive or negative causal links. Subsequently, we aggregated the cognitive maps across the homogeneous pools to build the diverse pool of local knowledge. This multi-level aggregation method led to a parsimonious and yet representative model of collective knowledge from a diverse crowd of stakeholders. Here, you can see this aggregated model of the diverse crowd. To test our hypothesis, we compared the accuracy of the models of homogeneous Grot versus the diverse Grot in two different ways. First, we obtained subjective evaluations and judgments from a scientific expert panel who independently assessed or judged the accuracy of the models. And second, we conducted an objective model evaluation using network analysis to determine to what extent the system complexities and sophisticated interdependencies were captured by each model. For the subjective evaluation, each expert participated in a semi-structured interview where they judged the accuracy of the 4 blinded models during an in-depth evaluation process. So they didn't know which one was which. Experts rated these 4 models regarding the accuracy of causal connections, of feedback loops, and these causal connections were ranked from very inaccurate to very accurate using a 7-point Likert scale. Box plots here show that show the distribution of judgments by all experts in the panel, and on average, experts ranked the diverse Grot model higher compared to models of homogeneous groups. We also compared the aggregated models regarding how they represented system complexities. To that end, we examined the network micromotifs or microstructures that are constructed by 2 or 3 nodes and some unique patterns of connections between them. Recent theoretical and empirical studies frequently suggested that 4 particular micromotifs may represent more complex patterns of causality, and therefore their higher prevalence and frequency in a cognitive map may indicate higher perception or cognition and understanding of complex interdependencies. These are bidirectionality, which represents reciprocal causation, multiple effects, which represent a potential trade-off or synergy in the complex system, indirect effect, which represents cascading impacts and path dependency in the system, and feedback cycles, which represents either reinforcing or balancing causal loops. We used uniform random graph tests to measure the prevalence of each complex motif in a cognitive map. Using this test, we measured the degree to which a particular motif was present in a map compared to its expected value in thousands of randomly generated graphs of the same size and density. Y-axis in these figures show the deviation of motif counts from their expected value. As you can see, among all models, the diverse Grot model demonstrated a prevalence above expectations for all complex motifs, and thereby showing a more adequate representation of complex interdependencies compared to homogeneous models. In addition to our experiment with actual human subjects, we also used the sample of cognitive maps to conduct Monte Carlo analysis. In these computational models, we made a large number of virtual agents whose cognitive maps were randomly generated. To produce these random cognitive maps, we used the probability distribution of stakeholder-driven cognitive maps for each type of a stakeholder. Using an agent-based model, we placed these virtual agents into many artificial groups with different compositions. And to measure the diversity of each group, we used Shannon diversity index and entropy index. Here you see 3 hypothetical examples from low to medium to high diversity. Similar to our experiment with actual human subjects, results of random experiments with virtual agents suggested that more diverse groups better performed in matching a scientific reference model, which is an ecosystem-based fishery management model developed by scientists at the United States National Oceanic and Atmospheric Administration, NOAA. So in this study, we empirically show that when dealing with a complex task, complex real-world problem, knowledge diversity is a form of ability which produces bonus and improves collective intelligence and the wisdom of the crowd when aggregating the local knowledge of people on the spot. At the end, I would like to express my deepest appreciation to my advisors, and a long list of collaborators for all of their support, guidance, and contribution to the study I presented here, and also the funding programs that supported my PhD and is supporting my ongoing postdoc. So I have a list of references here, and thank you so much. I would be happy to get questions.
Excellent. Thank you so much. Very, very interesting presentation. Thank you for that. So does anyone have some questions or comments or feedback for Payam?
How did you do the aggregation within and across the groups? Can you talk a little bit more about that?
Oh yeah, so let me go back to that. And then I just skipped all of these details because of the timing. So sorry about that if it's not clear here. Yeah, so we did the aggregation. If you look at the top of this figure, I explained that for the within the group we use the mean, and for across the group we use the median of the graph. So these are all graph aggregation techniques. And we in the paper, if you go to the paper, we explained in details why we did that, and we compare it to many different other aggregation techniques. This is producing the best results. So, and there are some theoretical explanations for that to balance out biases that may exist in each particular type of a stakeholder, like recreational fishermen think differently than commercial fishermen. They may have some kind of biases in their thinkings and mental models. So there is way to balance out these biases, and then this aggregation technique can do that.
Okay, I guess I'll just have to check the paper. I'm not quite sure how to take the mean of a mental map.
So basically, it's like a fuzzy cognitive map. So each relationship is either positive or negative, and then there is a strength of the relationship. So you do something like, if there is no relationship, so this is 0. If there is a relationship, it is something between 0 or 1. So you take the average of each relationship individually.
Were the nodes themselves constrained, or were they free text entry?
These are free, but we measured the number of unique nodes. It's something around 50 nodes mentioned by all samples, because they have a little bit of a structure, but we try to make, because we have another publication which is in Nature Sustainability. In that publication we had a defined number of nodes, and then everybody used only that nodes. But here we made them free, so they were free to use whatever they want. So they provided 50 unique nodes, but you can still see overlaps between between the maps. At least 20 concepts are overlapping in each map. Okay.
Okay, thank you very much. Yeah, I think that's one maybe to continue a little bit more on some of the side channels, and that was very interesting. So thank you. And it sounds like there's a lot more detail to unpack there as well. I think Takayuki is here. Sorry, there's I think been time conversion issues. Takayuki. Hey.
Hello.
Welcome.
Oh, hi.
I will hand over to you for the final paper, which is your paper with your student.
Okay, but it seems my student is not here. So, Julia.
Well, another thing we can do, if she's not here, we can ask her to record a presentation, and we can add it to the website afterwards. And then again, we'll create a LinkedIn thread so that once people have watched it in their own time.
Okay.
Because
Yeah.
at least that way she'll have a chance to present, and other people can hear a little bit more about the paper.
Thank you very much. Thank you very much.
You're
It seems it's Central European time, right? It's 2030. That should be 4:30 in Japan, and now it's 4:20.
It's okay. No harm, no foul. We can chat about it to the side anyway. I think then the best thing that we can do is we have a panel starting in 25 minutes. So what we will do is we will create some breakout rooms, and everyone can take a little bit of a break from their screens, or you can join the breakout room and have an informal chat with some of your peers and colleagues here. So I think the feedback was that we made the breakout rooms a little bit small the last time because a lot of people like to take a break. So we might make them a little bit bigger this time. Perfect. Okay, so enjoy the conversation and or the break, and we will see you back here in 25 minutes for our panel session on control, communication, and cybernetics from citizen science to citizen intelligence. Talk to you in a little while.